So we are with the second part of the machine chapter, and here we are going to discuss pulley today. So pulley is a metallic disc with grooved rim and a string or rope passed around the groove at the rim. The disc rotates about an axle. There is a disc, it is having a groove rim, a string or the rope passes over this groove rim, and the disc is capable of rotating about an axle passing through its center, and it can be fixed or it can be movable. That depends, and we will discuss each part of it. So a pulley can be of many types. This is a type of single pulley. One pulley you are using, so it is called single pulley. Single pulley can be two types. One is a fixed pulley, single fixed pulley. Other is a single movable pulley. So we will discuss single fixed pulley and single movable pulley one by one. So single fixed pulley is that pulley which has its axis of rotation stationary, is called single fixed pulley. So here a pulley is, the axle is fixed, so it is not rotating with the it is not moving with the load. Then a string passes over this pulley, and one end of the pulley load is kept, other end we apply the effort. The tension in the string will get distributed in the two strings. Since the same string is passed, so tension will remain same, so T and T we write. So here we get effort which we apply here is equal to T, and load is also equal to T, balanced by the same tension. So the mechanical advantage is equal to T by T, that is equal to 1. And if you observe here, the distance moved by effort, if it is dE or D, then the load will get lifted by the same distance, quite obvious here. So velocity ratio will be distance moved by effort by distance moved by load, that is also equal to D by D, that is equal to 1. Then efficiency is equal to MA by VR into 100%. So this is equal to also 100% in ideal situation. Actual case, it will be less than 100%. The reasons I have discussed in my previous class. So this is about single fixed pulley. One thing is quite obvious here, that in single fixed pulley we have though efficiency is equal to 100% in ideal situation, but the mechanical advantage is equal to 1. That means that we have to apply the same effort as that of the load. So why we will use this pulley? This pulley is used to change the direction of the effort to a convenient direction, because here you are using the effort in the downward direction, so in the direction of gravity, pull of earth. So one can use his own weight to lift the load. So that is the greatest advantage of single fixed pulley. Now let us move on to the single movable pulley. Single movable pulley. In single movable pulley, as the name suggests, the pulley is movable. That means it will move with the load. So suppose this is the load and this is a pulley. A string passes over this pulley, and one end of the string is fixed, another end we apply the effort. So in the direction of effort, the tension T here, the same string passes over it, so T. Now the load is balanced by two strands of the string, so L will be equal to 2T, and effort will be equal to T, because it is balanced by one strand only. So mechanical advantage will be 2T by T, load by effort, that is equal to 2. So clearly here the mechanical advantage is greater than 1, so it is a force multiplier. Now you see that if the effort moves a distance d here, both the strands of the pulley will move by the same distance, then it will cover up a distance t. So it will be d by 2 and d by 2. So if the effort moves a distance t, then the position of the pulley will be here. So distance moved by load will be d by 2. So distance travelled by effort, if it is d, then distance travelled by load will be equal to d by 2. In that case, velocity ratio will be d by 2, that is again 2. So efficiency will be 2 by 2 into 100%. Mechanical advantage, this is mechanical advantage and this is velocity ratio. So 2 by 2 into 100, that is equal to 100%. So this is the efficiency. Of course, this is the ideal situation. Now though we are gaining in force here, as the mechanical advantage is greater than 1, it is 2 here, but there is one disadvantage in this single movable pulley, that we have to apply the effort in the upward direction, which is quite inconvenient. So without changing the mechanical advantage, efficiency and the velocity ratio, we can change the direction of the effort by the use of a single fixed pulley. It often comes in the diagram, the diagram often comes in the examination. So you should practice this one. This is the movable pulley, one end of the rope is fixed, you have applied the load here, so this is the pulley. Now here you have to apply the effort. Before applying the effort, what you do, you pass the string over another pulley which is fixed. Now if you do this arrangement, then effort is applied in the downward direction. So T here, so same T will pass on here, same rope, so this will pass on here T. Now again load is equal to 2T because it is suspended by 2 strands of the string and effort is only a single strand. So the things remain same. That is 2T, L is equal to 2T is equal to T, mechanical advantage 2T by T, that is 2. And again the distance travelled by effort is d, then distance travelled by load will be d by 2. So the velocity ratio will be 2 and efficiency will be 100%. So it is just a arrangement by which we can change the direction of effort to our convenient direction without changing the mechanical advantage and velocity ratio of a single movable pulley. Now combination of pulleys we can use, and in this way we gain in mechanical advantage. So I am showing here there are some differences between single fixed pulley and single movable pulley, which is given in your book 1, 2, 3, 4, 5, 6, 7 also it is given, so you can do it from the book, you can read it. Now what I am trying to explain you is the combination of pulleys. Suppose one movable pulley is there, so when it is carrying the load L, then its strand, the second strand where we apply the effort, it is connected to another pulley, and it is again a strand passes over it, then the other end is connected to another pulley. This strand also is connected. Now in this way we have 3 pulleys. I can join more, but I am showing here for 3 only, and it is passed over a single fixed pulley. Now you know why single fixed pulley is used. The single fixed pulley is used here only to change the direction. Its work is nothing else. It is not adding any mechanical advantage. Now you see, if you apply the effort in this direction, downward direction, convenient direction, so T will appear in the string, the tension will appear in the string in the upward direction, the same T will appear here. Now it is passing over T here, so it will be T, correct? Now this strand is balancing the 2 strands of the upper pulley, so it will be 2T, then this will be also 2T, then this 2T plus 2T, this strand will balance how much? 4T, then this strand will balance 4T, then here the load is equal to how much? 4T plus 4T, so it will be 8T. So mechanical advantage is equal to load by effort if you do, so it will be 8T by T, that is equal to 8, which is 2 to the power 3. So 3 is the number of pulleys used, number of movable pulleys used. So here it will be 2 to the power n, where n is the number of pulleys. So you can increase the mechanical advantage infinitely by just joining number of pulleys by the formula 2 to the power n. Now what will be the velocity ratio? Velocity ratio will be also same thing. If the effort moves by distance d, then the load moves by distance d by 8 here. So it will be 8, and efficiency will be 100% for ideal situation. Now using several pulleys, this is another type of pulley, a combination of pulley. Combination of pulley is also done in another system of pulleys, which is called block and tackle system. In this system, there are certain number of pulleys. There are certain number of pulleys in each of the two blocks. One is the upper block, other is the lower block. The lower block of pulleys is a movable block, and the upper block is fixed. Generally, the number of pulleys in the upper block and lower block are equal, or upper block contain one more pulley than the lower block. Let us see that. So first, when the number of pulleys are same in the two blocks, upper block and lower block, this is the lower block where I have used two pulleys, and then the load is attached. The upper blocks are attached among themselves, which is fixed. Okay. Now when you pass the string out of it, then the string passes over from first pulley, and difficult holding the mobile in my hand to draw the diagram. Then this one, okay, so this is the, then here, then you see where it meets with the it is connected to the upper block, right? Now if you apply effort E here, the tension T here, the same string is passing over here, so this tension will be T, then this string, the tension will be T, this string, tension will be T, and this string, same string is passing, so tension will be T. Now load is balanced by 1, 2, 3, 4 strands, so L will be equal to 40. Now mechanical advantage in this case will be 4T by T. So this is equal to 4, where 4 is the number of pulleys. See here. Velocity ratio same way. If the effort moves by a distance T, then since the load is suspended by 4 strands, you can start from the with the movable single movable pulley. Here the load was supported by 2 strands, so effort moves by a distance d, then the load lifts by a distance t by 2. So here, if the effort moves by distance t, the load is supported by 4 strands, so it will be moving by distance d by 4. Understood? So this will be equal to 4. Efficiency is equal to 4 by 4 into 100%. So that is equal to 100%. Ideally, actually it will be less. So this is the formation of diagram or construction of diagram or sketching of diagram when both the blocks contain the same number of pulleys. 2, 2 I have shown, you can show with 3, 3 or 4, but remember one thing, that one end of the string we apply a foot and the other end of the string is connected to the upper block, the fixed block. Now let us see, when we take unequal number of pulleys in the upper block and the lower block, then what happens? So let us take upper block, there are 3 pulleys, and the lower block there are, it is getting shifted, okay, and the lower block it is having 2. The pulley sizes may be equal. I have shown it unequal for the simplicity or for convenience of my diagram. So I am now showing the like this, to this block, to this block, then to this block. Now where it will go? You see, it is getting connected with the lower block, the movable block. Unlike the previous diagram where the other end of the string was connected to the upper block. So when unequal number of pulleys are there in the upper block and the lower block, then the other end of the string will be connected to the lower block. Then here it will be connected to the load L. Apply the effort. Rest of the things are same. Apply the effort E here. Then tension, string is passing over, tension will be sheared. Here this string will shear, this T will be shearing, this is T and this will be T. So now load is supported by how many strands? 1, 2, 3, 4 and 5. So L will be equal to 5T and effort will be equal to T. So mechanical advantage will be equal to 5T by T, load by effort. So this is equal to 5. Velocity ratio, if the effort moves by a distance T, 5 strands are supporting the load. So distance moved by load will be D by 5. So it is equal to 5. Efficiency again is equal to 100%. Ideally, you see, I am always writing ideally 100%. How I am writing 100%? Because it is 5 by 5 into 100. Now you see here, when you are using machine, actually you are using the actual machine, and when you use actual machine, the efficiency will be less than 100%. Then when the efficiency is less than 100% in case of pulleys, in actual pulleys, when you are using, efficiency is never 100%. So it is less than 100%. Then what will be less? Suppose there are 5 pulleys. Then velocity ratio will be 5, mechanical advantage will be 5 for ideal case, and for actual case, if efficiency is less than 100%, then what will decrease? Mechanical advantage decrease, velocity ratio decrease, what decrease? So here you keep in your mind that velocity ratio is equal to the number of pulleys. So this will help you in drawing the diagrams also. Suppose I say that the number of pulleys or the velocity of ratio of the pulley is 3. Draw the diagram of the pulley system, block and tackle system of pulleys. So when the velocity ratio is 3 means there are 3 pulleys. So it will be unequal numbers. So 1 pulley more in the upper block. So it will be 2 pulley in the upper block, fixed block, and 1 pulley in the lower block, and you can draw the diagram. So the velocity ratio remains same. Only the mechanical advantage of the actual pulley system will be less. So here we are finding that in ideal situation, if there are n pulleys, ideally in ideal situation, if there are number of pulleys used in the block and tackle system, if it is equal to n, then ideally mechanical advantage is equal to n, velocity ratio is equal to n, and efficiency is of course 100%. But in actual case, what you cannot be sure that mechanical advantage is n or not. So in actual case, mechanical advantage may not be n, but velocity ratio will be definitely n. Velocity ratio will not change. Then in that case, what you can write as? So suppose why mechanical advantage will not be there? So because of weight of the moving parts of the machine. So in that case, what we write that suppose we were writing this as T is supporting the load effort and NT is supporting the load. So in this case, what we will do? Suppose X is the moving part of the machine. So total load will be NT. N is the number of pulley or number of strands supporting the load into T plus X, and effort will be here T only. So here you can write L by E, which is the mechanical advantage, that is equal to NT plus X by T. So it will be L by E is equal to NT by T plus X by T. T cancel. So L by E, or I am writing here. So L by E is equal to N plus X by T, or L by E is the mechanical advantage. Ideal mechanical advantage is equal to N plus X by T. In place of T I am writing E. So N is equal to ideal mechanical advantage minus X by E. So this is the mechanical advantage. N is the mechanical advantage, actual mechanical advantage, which is ideal mechanical advantage minus x by E. So here this one can be done in other way also, as it is given in your book. You can see that if E is equal to T here, E is equal to T here, and then you can do in the other method as E is equal to T. So L plus W in place of writing N plus T, I did in another method, L plus W. So load plus W is equal to NT. That is the better way, is equal to NT. Now L plus W by E is equal to NT by T. So TT cancels. So L by E plus W by E is equal to N. Again here you can write that L by E is equal to N minus W by E, where W is the weight of the moving part of the machine. So it is actual mechanical advantage, again it is coming equal to ideal mechanical advantage minus weight of the machine by effort. So it is something less than the ideal mechanical advantage, it is subtracted. Now if you put in the efficiency, suppose in place of W I write it as X. X is the weight of the moving parts of the machine. Then efficiency will be equal to, actual efficiency will be N minus X by E, that is the actual mechanical advantage, by velocity ratio, that is N. So it is N by N minus X by NE, or it is 1 minus X by NE. So definitely it is less than 1, means it is less than 100%. So that is it. So greater the efficiency, the pulleys in the lower block should be as light as possible, and the friction in the bearings of the pulleys should be minimized by the use of lubricants. Now students, you have to do the question answers. I tried to explain the chapter, and now you have to work it out, and then you have to do the numericals. In case of doubts, you can ask me. Thank you.